In this recording, we will be talking about performance evaluations. In this specific section, we are going to assess the predictive performance of data mining models, including the linear and the logistic regression models, the ones that we discussed earlier in the previous chapters. Recall that it's important to develop performance measures that evaluate how well an estimated model will perform in a previously unseen data set, rather than just making the evaluation solely on the basis of the sample data used to build the model. In previous chapters, we discussed cross-validation techniques, where we partition the original sample into a training set to build or train the model, and a validation set to assess or evaluate the model. We also used root mean squared error, RMSE, to evaluate linear regression models, and we used the accuracy, sensitivity, and specificity rates to evaluate logistic regression models. Here we are going to extend this on data partitioning and include more other performance measures that can be applied to all supervised data mining models. Number one, we are going to go and talk about data partitioning. What is data partitioning? Data partitioning is the process of dividing a data into a training validation. In some situation, we create another set called test data set. So 3, sometimes 2, sometimes 3. A common data partitioning practice is a two-way random partitioning of the data to generate a training data set and a validation data set. We use random partitioning as opposed to fixed draws. In one of the examples we did a fixed draw. No, in general we're going to do random partitioning to avoid any bias in the selection of the training and validation data sets. The training data set, which contains the larger portion of the data, trains data mining algorithms to identify the relationship between the predictor variables and the target variable, which is the response variable. So the target variable is our response variable. And the validation data set, which is not involved in the model building, is used to what? Is used to provide an unbiased assessment of the predictive performance of the data mining models. The model built from the training data is used to predict the values of the target variable in the validation data set. These predicted values are then compared to the actual values of the target variable of the validation data set to evaluate the performance of the model. We did all of this in the previous examples. The performance measures obtained from this process can be used to help assessing model performance, number one, fine-tune the model, number two, compare the performance of competing models, this is number three. So what is the common practice? The common practice is to partition 60% of the data into training data set, maybe 60, maybe 70 in some of the other resources, and 40% of the data into validation data set. However, sometimes the 70-30 training validation partitioning is used if the model is building process can benefit from a larger training data set. So 70-30 maybe. And we can implement cross-validation with the handout method or k-fold cross-validation method. In supervised data mining, we sometimes use a three-way random partitioning of the data to generate training, validation, and test data sets. The test data set is relevant when the validation set is used for fine-tuning the model, and the third data partition, which is the test data, which is not involved in either or both of them, the model building or model selection, is created to evaluate how well the final model would perform on a new data set that has never seen before. So in the case of the two-way partitioning, the data are usually partitioned randomly into two or to create unbiased training and validation sets. In the three-way random partitioning method, usually we have 50% training, 30% validation, 20% test. In this class, what we are doing only two-way partitioning just for the training and validation. Sometimes the target class that we wish to classify is very rare. And we had an example about this. Default on loan, right? This reduces the usefulness of classification models. For example, in order to build a classification model that informs an online retailer about which prospective customers are likely to respond to a promotional email, the retailer conducts an experiment by sending promotional email messages to 10,000 potential customers, of which only 200 customers respond. Look at the rate. Only 200 responded out of 10,000 customers. So we have data about the 10,000 and only 200 responded. So this results in a response rate of 2% only. So the resulting data from this experiment would consist mostly of what? Non-responders with a little information to distinguish them from the target class of responders. If this retailer attempts to build classification models as we did, the best performing model might be the one that suggests no prospective customers will respond to the promotional email message, as the model would have an extremely high accuracy rate, 98%. And this is exactly what we had in our example, the one we did in the logistic regression about the default on loans, right? Nevertheless, the best performing model in this application might be useless to the retailer. So what to do is oversampling. This is a common solution. The oversampling technique involves intentionally selecting more samples from what? From one class than from the other class or classes in order to adjust the class distribution. So you have adjusting the class distribution of the dataset. The rare target class, which is this one, cases, will be more represented in the data if they are oversampled. This would lead to predictive models that are more useful in predicting the target's class cases. In our example, in the promotional email example, the retailer may choose to oversample the rare target class cases by including most, if not all, responders and reduce the number of non-responders, so that the resulting data set constitutes a healthy combination of both responders and non-responders. Note that, as a common practice, only the training data set is oversampled. This is a common practice. Okay, it's a common practice. Observations in the validation and test data sets, if you have three-way of partitioning, maintain the original class proportions so that the resulting performance estimates will be more representative. If we go back to chapter 7, we used goodness of fit models like R-squared, adjusted R-squared, to assess how well the regression model fits or explains the variation in the target variable. Nevertheless, the model that fits a set of in-sample data well may not predict new observations accurately due to the possibility of overfitting. This is an overfitting model. What is overfitting? Overfitting occurs when a model corresponds too closely, look at this, too closely to a set of data, but fails to predict future observations reliably. So it's too closely to the data set, but it fails to do a good prediction. This is underfitting, by the way. This is good fit here. So in other words, the overfitted model accounts for the noise. Yeah, this accounts for the noise in a particular set of data rather than the underlying patterns that can be generalized to future observations. It's not looking for the pattern here. He's looking for just the noise. He's just following the data. This is a pattern. So we see the overall pattern of the data. Overfitting may become more severe as the model complexity increases. So this is important. If you prepare a complex model, so we're going to have an overfitting problem. So that's why we have to have a balance between we call it a trade-off between the variance and the bias. Data partitioning, so what to do? We have let's say, overfitting problem, so what to do? Data partitioning and the cross-validation can be used to detect overfitting and provide objective assessment of the predictive performance of the models. So these two techniques can be used to detect overfitting and give an assessment of the predictive performance of the models. Suppose a model is developed using a training dataset and is then assessed by inspecting the performance measures obtained from the validation dataset. While the performance of the model on the training dataset tends to improve as the model gets more and more complex, let's look at this. Yeah, the model performance on the validation dataset will improve initially, but deteriorate after a certain point. As we can see, the error rate goes down. Here, the error rate goes down for the validation error, then start going up, right? The error. In addition to providing an unbiased performance evaluation of the model, the validation dataset is used to identify the optimal model in some supervised data mining techniques. So here, if you look at the model complexity, as the model becomes more complex, we have low error for the training, but for the validation, look at the error goes down until when the model is simple, we have high error. When we build more complex model, so at this point, maybe it's going to be the optimal model complexity point. We have relatively low error at the same time. We don't have a very complex model that may result in an overfitting problem, because look at the error here for the training data. It goes to 0, right?